Hello everyone. We are Group C and the purpose of our presentation today is to discuss our work on the internal hardware of the Super Brute jack. The Super Brute is the newest iteration of the Husky Brute jack from Husky Towing's product line. The Super Brute will be updated and streamlined to reduce reliance on mechanical components by using electrical alternatives, which will reduce wear and tear as well as drive down production costs. New features for the latest model will include integrated external RGB LED and floodlight ports for simple plug-and-play use by the customer, as well as an updated interface of the mobile application for controlling and monitoring the Super Brute jack during operation.
For the requirements, the device needs to have the ability to extend and retract the jack through the Android/iOS Super Brute app via Bluetooth, or by using the physical controls on the jack itself. It should also have the ability to control the RGB LEDs plugged in by the user and change their color through the app. It will also have safety features that protect the user and the device, such as motion sensing, direction of rotation sensing, connection timeout shutoff, and a mechanical brake. The Husky Super Brute uses a brushed DC motor that operates at 12 volts and a 20 to 30 amp operating current range. It can operate all the way up to 60 amps where it reaches destruction current. The lifting capacity of the jack is 5,000 pounds. It uses Bluetooth Low Energy, which has a radius of 50 feet. It has a trailer wiring connector for the floodlight and the 4-pin main and lock connector for the RGB LEDs.
The design approach for this project was influenced by the sponsor, RV Intelligence, and the customer, Husky Towing Products. The customer wants the system to be placed within their RV jacks to control the extending and retracting of the jack. There are certain design specifications that cannot be changed because our system must be placed within their products. There are three main functions that we needed to consider when designing the system. The motor needs to be controlled to extend and retract the lift. This can be done with a brushed DC motor driver. To detect the direction that the motor is spinning, we will use a Hall effect sensor placed near the motor. With this data, we can also calculate the speed of the motor. The brushed DC motor has been provided by Husky Towing because the motors are already inside the jacks. Another necessary function to consider during the design process is the Bluetooth connection. This connection is very important because it is the primary user control for the motor. A mobile application has been designed to extend and retract the jack with an easy user interface. To ensure that the jack is level, we had to design a way to gather coordinate data. An accelerometer is a great way to determine the orientation of a device. If the jack is not level or it's in motion, it will not be able to extend. This will be an important safety feature in our design. An important aspect we needed to consider in the design phase was the dimensions of the Husky jacks. Our entire PCB, motor, and wires must fit within the dimensions shown here. The wiring within the jacks already exists, so we have to design our PCB with connectors that correspond to these wires. To accomplish the motor control, we chose the TLE 92108 motor driver and the AH3774 Hall effect sensor. The motor driver is the largest component we will have on our PCB and was only released in 2019. The next largest component is the Bluetooth module. We chose the CYBLE 212006 made by Cypress because of its programmability. We can program this device to control the other devices through SPI communication. For the accelerometer, we chose the BMA 456 because it is very small with low power consumption. This component can collect coordinate data, detect motion, and measure temperature. This is a simple block diagram showing how these components will be connected. The CYBLE is a wireless module solution that offers more than just Bluetooth. It will be the main controller in the PCB. Using Cypress's IDE, PSOC Creator, the team has been able to program this device to send instructions to all the other components. The CYBLE will send signals to the TLE motor driver to determine if the RV jack should be extended or retracted. The FET network seen in this diagram is a MOSFET network comprised of 8 half bridges. The FET network will be used to power the DC motor, emergency brake, and LEDs. This is a more detailed block diagram elaborating on the one shown previously. You can see that the main components are still connected the same way with the CYBLE in the middle. This does not represent the actual PCB layout of our system, but it does show the connections and voltages needed for each component. On the bottom left corner, you can see the DC input. This voltage will be passed through a fuse and then to an overvoltage protection circuit for extra safety. Since we do not need 12 volts for all of the components, we will have a voltage regulator to decrease the voltage from 12 to 3.3 volts. This 3.3 volts will be used to power the Bluetooth, accelerometer, Hall effect sensor, and motor driver. In this diagram, we have included the connectors to connect the PCB and the RV jacks. The first connector with 6 positions will be used for the external switches. We will leave 3 connectors empty for extra connections later. The second connector with 6 positions will be used to connect the LEDs and the emergency brake. In this diagram, the floodlight refers to the external work light on the jacks. Above this diagram, we have added a magnet to signify that the Hall effect sensor will be measuring the magnitude of a magnetic field. In the actual PCB layout, this Hall effect sensor will be placed closer to the motor.
Here we have the unfinished schematic. First, let's talk about the connectors. In total, we need 4 connectors for this project. 2 6-position connectors, which are surface mounted, and 2 2-position connectors, which are through-hole. The first 6-position connector is going to be rated at 1 amp. This is mainly for the manual switches. We have a total of 3 manual switches: extend, retract, and the light switch. As you can see here, this is the input connector. One pin is connected to the extend on the microcontroller, the other is connected to the retract on the microcontroller, and the third pin is connected to the PWM pins on the microcontroller that control the lights. For this connector, we chose the main lock 2922306 connector, which has a current rating of 1 amp and a maximum current rating of 2 amps. The second 6-position connector is mainly for the external lights themselves: floodlight, internal LEDs, and the brake. Four of the positions in this connector are going to be the lights: the red, green, blue, and white. The fifth pin is going to be connected to the floodlight and the internal LEDs, and the 6th pin is for the brake. This connector is going to be rated at 25 amps. The other 2 connectors are through-hole, 2 position each. These are for the power supply. One connector is going to be connected to the input power. One pin is for the 12 volts input and the other pin is for the ground. The other connector is going to be connected at the end of the other side of the board. It's going to be connected to the DC motor. One pin is for power and the other for ground as well. This one is going to be rated at 10 amps at 12 volts. This is one of the 4 connectors. We are missing 3. We haven't decided which connectors we're using yet. This is the overvoltage and reverse voltage protection circuits. So we didn't use the reverse voltage protection circuit that are included in the TLE driver data sheet. That one also didn't have an overvoltage protection. So through some recommendations and advices, we used this circuit. We designed this circuit so that the maximum power is not going to exceed 18 volts. As you can see here, through simulation, we tried to cap the voltage at 18 volts. The maximum voltage rating of the TLE is 28 volts, and the average operating voltage is between 12 and 16 volts. Since in many applications the TLE is going to drive more than 16 volts, we capped the voltage at 18. Also, in very rare occasions, the voltage is going to exceed 18, but it's not worth the trade-off to increase the cap, because if we do so, we have to modify the other components so they can handle more power, which can be a little more expensive. Here we have the voltage regulator and the hold-up circuit. The voltage regulator is going to be apart from on semi. It is to convert 12 volts in the 12 volt input to 3.3 volts for the low voltage components, which are the microcontroller, the accelerometer, and the Hall effect sensor. The regulator can handle up to 20 volts input, which is good enough for us since our voltage is not supposed to increase beyond 18 volts. Also, we have the hold-up circuit, which is a bunch of decoupling capacitors in parallel, just to filter out the noise coming from the 12 volt input to the regulator. This is the TLE driver, the shunt circuits, which we copied from the TLE driver datasheet. Here we have the accelerometer, the microcontroller, and the Hall effect sensor. We also have all the FETs on the right. So since we're driving 12 volt DC motor, we use bigger FETs which can handle more voltage and more current. We picked the FETs from Infineon. They have a continuous drain current of 100 amps at gate to source voltage of 10 volts. It also has a maximum drain to source voltage of 40 volts. So when we started choosing footprints for the passive components, we first located the components, calculated how much voltage that will be at that component and how much current will flow through it. We then looked up for components that have the suitable parameters with reasonable prices and match their footprints. So we're still missing two position connectors at 10 amps and one 6-position connector at 25 amps. We're also missing the LEDs, the schematic for the LEDs.
As for the software design, the main program operation will go as shown in the following flowchart. First, we will begin by initializing all of our components, enabling interrupts, and starting the SPI and UART. Then we will go into our main loop. We begin by checking the connection status of the device. If the device is connected to a phone, it will then run the function flag handler. This function checks if any of our flags have been set by the interrupt lines and calls a function to handle it. After all the flags have been taken care of, we can start the main loop over again. Taking a closer look at the main components in our design, let's start with the Cypress CYBLE212006, which we chose as the microcontroller for our board. It has many great features that will help us get the most out of our design. It has 2 serial communication blocks supporting I2C, SPI, or UART. It has 4 dedicated 16-bit timer, counter, or PWM blocks, which we will be using for the RGB lights. It has remappable pins, which gives us the flexibility to make our design as optimized for space as possible. And it also has a BLE protocol stack supporting generic access profile. We wrote drivers for our other components to work with the CYBLE and loaded them onto the module. At this point, our code uses 40% of the memory, which gives us room to add more functionality and revisions in the future.
Our design requires a full N-channel bridge to drive the motor, as well as a few half bridges to drive various components, such as pulse width modulated LEDs and an emergency brake. To fulfill this requirement, we chose the TLE 92108-232QX, which is a multiple MOSFET driver that can drive up to 16 external N-channel MOSFETs. The TLE also comes with many other built-in features, which include reverse battery protection, 2 configurable current sense amplifiers, outstanding low sleep current, and advanced protection and diagnostic, which makes the device ideal for use in any type of motor-based lift. It has drain source monitoring for hard short circuit detection and current sense monitoring for soft short circuit detection, over temperature warning and shutdown, as well as detailed off-state diagnostics such as open load, short circuit to battery or to ground via the 24-bit serial peripheral interface. For testing purposes, we use the TLE 92108-23QX app kit, which offers an easy method for connecting to the microcontroller for debugging the TLE IC. This is done through the aforementioned 24-bit serial peripheral interface, or SPI, which enables the communication between the microcontroller and the TLE through the UIO stick interface, as well as using the SPI header found on the app kit to monitor data transfer, which allows us to verify correct bit flow values on the SDI and SDO lines. The MOSFET driver IC acts as a SPI slave, while the microcontroller acts as a SPI master. Through the SPI, we can read, write, and clear multiple registers in the TLE quickly and efficiently, which allows for easily configuring the many instructions we will need to create to carry out multiple tasks the TLE will need to do, such as power on initialization, extend retract the motor, control the brightness of the LEDs via the PWM channels, and persistent status checking to ensure everything driven by the TLE is working as intended.
For the accelerometer component, we chose the BMA456 from Bosch SensorTech. This is a triaxial acceleration sensor that measures coordinates in the XYZ plane. This sensor can be programmed to fit our needs. For example, we were able to program the output data rate to a low frequency of 12.5 Hz. We were also able to configure our power mode to either performance mode or low power mode. In low power mode, the accelerometer periodically switches to a suspend power mode, in which no data is measured. We wanted our data to be as current as possible, so we chose performance mode. The sensor has a digital interface that can be configured for SPI or I2C communications, and for our application, we chose SPI. The BMA has two interrupt pins that send data to the CYBLE. The on-chip motion interrupt is triggered if the accelerometer senses motion. This will be used to stop the motor from running if the jack is in motion. The new data interrupt constantly sends new coordinate data to the CYBLE to ensure that the jack is level. The accelerometer is actually a very small component. To program this, we use the Bosch SensorTech shuttle board. This board is a PCB with the BMA456 mounted onto it, as seen in the second photo. The accelerometer is the small black square below those four pins. This shuttle board allows us to easily access the sensor pins to program the interrupts and SPI communication. In the photo on the right, you can see the CYBLE development board in the foreground. It is connected to a computer using the Cypress Mini-Prog4 debugger and programmer. In the background, you can see the BMA456 shuttle board connected to the CYBLE. This is the method that we have been using to program and debug our components.
We faced a few difficulties while working on this project. The pandemic caused delays in the development kits being delivered to us and led to the team being unable to meet in person and work on the project for the first few months. Some of the components that we're using don't come with drivers, and our team had very little firmware coding experience before working on this project. So writing the drivers for the components was challenging. We also had to use software tools that are standard at RV Intelligence that we were unfamiliar with. For example, we had to use KiCad and PSOC Creator instead of Eagle or Code Composer Studio, which we were taught how to use in class. The main difficulty that we faced is that the project changed a significant amount. Originally, our objective was to make a boat lifting device that we picked parts, designed the circuits, and wrote an app for, but our objective changed to making an RV jack. This led to us scrapping all of our board designs and code and starting over. Despite all that, we had a good amount of success so far. We didn't have to start from scratch, as we were able to use some of the same components from the boat lift device to make the RV jack, such as the DC motor and the BLE module. We replaced other components to add features that better fit the new device. And at this point, we have finalized our design, we've tested all of our components, they work as intended, and they're all communicating with each other successfully. We also wrote the drivers for the components, and the device already has some basic functionality such as extending and retracting through Bluetooth.
The project has been decided upon by the project sponsor, who dictates the overall budget and financing. Currently, the total cost to date is roughly $40 per completed PCB, plus the cost of the jack for testing at $270, which results in a total investment of roughly $310. Unless further optimized, no changes are scheduled to occur in the foreseeable future that could impact our budget or design. The ultimate goal is to reduce the cost of completed PCB production from its current value of roughly $50 per PCB to $30 to $40 per PCB by the time the product is finalized for distribution. Our team has been making steady progress, and we are optimistic that we will finish our project in a timely manner, even given the circumstances with the scope of the project changing relatively late and COVID being a factor that affected our ability to have group meetings. We are all but done with research and PCB design. We still have room to improve the hardware choices and software optimization, but these are not factors that will currently affect completion of the project if we leave them as they currently stand. Most of our time now will be allocated towards debugging the software, mobile app integration, and simulations to verify everything works given any possible situation a Super Brute may come across during operation. Our project timeline will be a strict guideline for us to adhere to so that we can monitor progress and finish this project in the allocated time frame. As of this presentation, we are currently debugging the modules that will be used on the PCB, which will be a major milestone when completed. Once the PCB has been assembled, we will program and debug the modules on the PCB and then test it in a working environment by installing it into the Super Brute Jack and running several stress tests and diagnostics checks to verify everything is functional and within standards. From here, we will integrate the updated mobile app and test that all functionality done previously through manual operation can be done with the mobile app as well. Lastly, we will perform many more stress tests on the finalized package as a whole to see if there are any faults or failures we need to address. When we see that everything works with a perfect success rate and the sponsor has given his approval, we will have a completed project ready for presentation and ultimately distribution. This concludes our presentation on the internal components that we have been working on for the new Super Brute Jack that will be distributed by Husky Towing in the near future. Thank you all for your time and attention.